My name's John Anderson. I'm a co-principal investigator and one of the authors of the modules in our Aerospace Manufacturing Education Project. This is a National Science Foundation funded project, and our main product is educational modules that you can use to insert into your courses. We want to talk about why you might like to do that and how you might use those. So, to give you a feel for what sort of materials we have available out there, this is a list of our current modules. We probably have another 10 to 15 modules in the works, and they'll be out sometime in 2012. So right now we have a series of composites modules available. We have an introduction to composites, we have a composites manufacturing module, and we have a composites repair module. We also have a series on materials, and one of those is failure analysis. We have some other materials courses in the works that'll be, or modules I should say, not courses, that will be available in 2012. We have 4 fastener modules. We found that one of the things that new engineers found lacking in their education, that is, new engineers that were working in the aerospace industry found lacking in their education, was more detail on fasteners. And so we have 4 modules on fasteners. We have an assembly module, and we have 4 composite labs. We'll talk about the labs a little bit later. First thing I'd like to cover is the criteria that we use to design these modules. First of all, these are open source. You can go to our website and download the modules and all the materials that we have. It's free to users. That is, if you're going to use this material in an educational environment, there is no cost to you. Also, we decided consciously to do this in a PowerPoint and Word format, as opposed to trying to put it into a PDF format, so that it makes it easier for you to use either the complete module or parts of the module, or add in your material. So we're trying to make it as flexible and as user-friendly as possible. All of these modules are designed roughly around 2 to 3 hours of lecture. That is, you typically either have a 50-minute or a 75-minute lecture period, and these are designed, you either have 2 of those, 2 75-minute lectures or 3 50-minute lectures per 3-hour course per week. And so these materials are designed roughly to fill up 1 week, so 2 to 3 hours of lecture. They're targeted to fit into 100, 200, or early 300 level engineering or technology courses. So they're suitable for a community college environment or a university environment in the freshman and sophomore years. We're trying to make these modules instructor friendly. Our purpose is to offer you a product that you can fit into, for instance, your survey of materials course, 200 level survey of materials course, that minimizes your preparation time and allows you to have a high quality material to either hand out to your students or to use in your lectures. The reason that NSF funded this is we're trying, our overall goal is to try to influence your students to consider airplane manufacturing as a career choice. And so, although these modules can fit into a general materials course or other general technology and engineering courses, the specific examples that we use are aerospace manufacturing. So perhaps the easiest way to demonstrate this the design of these modules is to actually go through parts of one of these courses or one of these modules. And I've selected the Introduction to Composites. This is 2 to 3 hours of lecture, and it's designed to fit into a 200 level materials course. Most of these materials courses now have a section in or chapter in your textbook or a section in the course for composites, and you can fit this introduction to composites in to satisfy that requirement. So let's start out first by looking at an overview of the course. And this also is the first slide after the title slide in the PowerPoint for this module. So the course overview, we're going to go through some composite material structure and explain what it is. We'll talk about material components, both commercial components and in general what materials we're going to use in composites. We'll talk about aluminum versus composites. Typically for composites, for fibrous composites, we are designing for a low weight and a high strength. And in the past, those applications have largely gone towards aluminum or titanium, aluminum being the more cost-effective, or at least the least costly of those two components. So we'll compare aluminum versus composites. And we'll talk about some of the advantages and disadvantages of composites in aerospace applications. We'll look at some composite applications, and then we'll look at composite manufacturing techniques as a survey. And then we'll talk about some subsequent composite modules. So it's important to note that all of the authors of these modules are actually instructors at the community colleges or universities that make up the partner institutions for this grant. So the folks who write the modules actually use them, and they have some experience and some knowledge of what your needs specifically are as an instructor. So we have two documents that go with each module. One's PowerPoint that you can use directly in your classes, and the other is a set of instructor notes. And our intent is that you can spend a minimal amount of prep time reading the instructor notes and be able to do a credible job using the PowerPoint module that we give you to cover this material. So this is the instructor notes. All the instructor notes start out with a general description of what this module does and references the National Science Foundation award number. And then we go into learning objectives. So you can take these learning objectives and stick them directly into your syllabus for your course. Again, this is a Word document, so you can cut and paste this as part of a larger set of learning objectives for your entire course, or select the ones that you want. We also have a set of prerequisites, and so this is set up like a normal syllabus that you would find in the course. After those two items in the instructor notes, we talk about individual slide notes, and we'll see that as we go through the course. But the slide notes have the slide number and then the description of what information that slide seeks to pass on, and any other activities that we think that you might want to consider in using with your students. So the first thing we'd like to do here is go through some of the individual modules and talk about how those modules are put together. We use, of course, different techniques to try to pass along information. Some of them are graphical, some of them have only words. But we'll look at several slides as we go through to give you a feel for how we put them together and how you might best use them. So the first is an introductory slide to the materials part of the module. This is fiber reinforced plastic, FRP composites, and that's all we'll be talking about in this module. It talks about how they're made. They consist of two materials, a plastic matrix and the fibers. And then we talk about what each of those components offers to the overall material. Next, to continue along that same thought, we have a graphic that shows how you combine this plastic and the fibrous material into an overall composite. So this is fiber reinforced plastic composites continued. And you'll see later in the slides, we try to use a lot of real life imaging. So you'll actually see composites being made, or you'll see the part, or you'll see the machinery. And I think that's very instructive in imparting to the students a sense of how the theory actually works in real practice. But sometimes you need to fabricate a graphic that gets the idea across, and we want to make sure that they understand this contribution of fibers versus the plastic and how those two work together. So in this case, we made our own graphic to illustrate that principle, and you see that here. I would also like to point out in the lower right hand corner of this slide is a copyright notation. We did copyright our materials, but that's not to keep you from using them however you like in an educational environment. We just wanted to make sure that that these materials weren't used in a commercial environment, primarily because we have permission to use a lot of the graphics only in an educational environment. So we can't pass on permission for you to use things that we only have permission to use in an educational environment. Concepts of the materials. We want to talk about the real life applications. What does this stuff really look like, and what sort of materials are actually used in real practice? So commercial fibers are available in several formats. First is a yarn, and that's a bundle of fibers twisted together. Tow is a large bundle, and a roving is a large bundle of fiberglass. Tow is a large bundle of carbon fiber. So you can also get unidirectional tape or woven fabric or mat. And we show images actually from vendors of real commercial materials. And in the instructor notes you're going to see later for this slide, we reference the vendors' websites so that you can have students go there and actually look for real life materials. This slide, aluminum versus composites, talks about one of the important considerations in designing composites or in using composites in an overall product or machine design. Going back to the previous slides on the materials, we said that the strength of the composite comes from the fibers themselves. Well, those are along the axis, the strength is along the axis of the fibers. So it's very important that we orient the fibers in the direction that we need to withstand a stimulus to failure or a force. Aluminum, on the other hand, is an isotropic material, which means it has the same properties in all directions. So it's a different design philosophy in designing a part out of aluminum than it is out of composites. And that also means that the manufacturing process for composites is very important, because we have to make sure that the fibers are laid in the direction that we want the final strength of the part to exist. Now that we've set the stage by talking about the materials, we can talk about how you actually go about building a composite parts. And so this slide shows on the left hand side an actual part being laid up. And on the right hand side it shows a graphic for that whole process. So we laminate and lay up the woven fabric containing the fibers. We put that into a mold. We apply the resin to it, and we apply heat and pressure. We cure it, and then we demold the part. And we're going to go through and talk about each of those parts of that process in more depth. So the first step in this process is to arrange the fibers in the orientation that we want them in the final product, and to apply the resin or the plastic that's going to be the matrix that holds these fibers in place. So this slide is probably the most basic process that we use is a wet layup, hand wet layup. And so this slide describes that process in the individual steps. Now that we've described the process and when the students have a feel for the overall way that we put this together, we want to show some graphics to reinforce that. So these are actual molds showing on the left side the dry woven fabric laid up into the mold, and on the right side this is the fabric impregnated with resin. So describing the process in words and then backing that up with a visual image of how the process works in a static picture is probably the classic way that we present materials in a lecture environment. The instructor notes, if you go, these are the actual instructor notes for the slides you just saw. So these describe in slide 25 the picture that you saw, the static pictures, but in slide 24, after the process, the word description of the process, we reference a YouTube video that you can show to your class of the entire wet layup process. And this comes from one of the vendors for these resin and fiber materials, Airtech. So this is, and they make this video available on YouTube. You'll see as we go through the instructor notes, we use YouTube a great deal. Now anybody can go to YouTube and pull up these videos. The time-consuming part of doing that is to sort through the videos, find the ones that illustrate the principles that you want to show, and find the ones that best encapsulate that. So we've tried to shorten your prep time by going through and finding that material, doing that legwork for you up front. So once we get the fibers and the plastic resin into a mold, we need to consolidate the materials. That is, we need to debulk the materials. We need to get all the air bubbles out of the plastic matrix, because remember, we want to hold the fibers as close together as possible, and we want to make sure that all of the matrix material is actually resin, it's not just air in there. So we want to debulk the part. That is, we need to put a uniform pressure across the part that pushes it into the mold. And the way we typically do that is vacuum bagging. And this image shows a vacuum bag being applied over the mold. The image on the left, the cutaway, shows all of the individual components in the vacuum bag process. The image on the right shows the actual process as it's done. And so as we go through the instructor notes, we listed where these components can be found. We've also listed videos of the actual installation of the vacuum bag onto a part. So once we've made the part, once we've laid the fabric down, we've put the plastic in, we've put a vacuum bag over the material so that we get uniform pressure, and we've debulked the material, we have it in its final configuration. We have the plastic and the fibers in the mold in its final configuration, and now we need to cure it. There are two issues in curing. As we cure, curing typically implies that we're going to either allow this material time to cross-link, these are thermoset plastics, So we allow them time for the chemical reaction to go forward, for them to cross-link, and we accelerate that reaction by adding temperature. At the same time, we want to control the part so that it stays in the same physical configuration that we started out in. So an autoclave is a fancy name for a pressurized oven. And we essentially roll the part into the autoclave, we raise the temperature, we raise the pressure, we cause the reaction to go forward fast so we get a strong part quicker, and we hold it under pressure so that we control the part dimensions in the mold as we cure it. The autoclaves, if you think about large parts in the aerospace industries, if you're going to cure a large part as one entity, you need a big oven. And that's what these images show. You can see in the top picture there's a guy standing in one of these autoclaves. This is by far not the largest one out there. Boeing has some huge autoclave ovens they use in their commercial products. So the ones on the left give you a sense of the size and the scope and what the actual machine looks like. And on the right, we have a diagram that shows the controls for the oven with the part in there and how the whole system works. So we can see from the previous slides there are some issues around manufacturing composites. The wet layup process is very expensive. It's very expensive because you have to have people there actually orienting the fibers. There are some tools that we can use to help people do that, but it's very labor intensive still. So how do we get around that? The other issue is the autoclave. The autoclave is a very expensive machine to purchase. It's a very expensive machine to run. So there's a lot of work with the chemistry of the plastics, the way they cure, to do what's called an out of autoclave curing process. But we need manufacturing methods that help support that effort. So the first thing we're going to attack is how we put the plastic into the onto the fibers. If we just take a brush, for instance, and do a wet layup, so we lay the fabric onto the mold, we take a brush and we brush on plenty of plastic, and then use our vacuum bag to push the excess out of the way, we've wasted a lot of plastic and we've caused a trimming process to have to be done in the final cured part. And then there's the question of what do you do with the cured trim material. Since it's a thermoset, it can't be easily reused. So one process that's an improvement on the hand layup, the wet hand layup, is called vacuum resin infusion. You'll see various names attached to this, but this is the basic process. We orient the fibers in the mold. We lay in the plastic fabric, or however we're going to form those fibers so that we get our final orientation. And then we bag it up. We use a vacuum process where, if you look on the image on the top left side, you'll see a vacuum line coming out of the top right of the image, and a supply of resin over on the lower left. Well, the vacuum bag that covers this whole thing is airtight, or vacuum tight, I should say. So when we put vacuum on one side, we suck the resin up into the bag through and around the fibers and out the vacuum line into a reservoir. So we're only putting in enough material, we're pulling a vacuum at the same time so that the vacuum bag is pushing down on the fabric, and there's only enough room to put the plastic resin material that we're actually going to use, and it's very evenly distributed. So we see on the right a photo of some vacuum resin infusion parts in manufacture. So our vacuum resin infusion addresses the problem of excess resin and the distribution of resin through and around the fibers. But it doesn't address that laying down of the fibers, the orientation of the direction, and that's the time-consuming part of this wet layup method. So the industry is constantly looking for ways to remove that manual action in the layup process and to make the throughput of those parts faster. And so one of those, obviously the way we go at that is automation. So how do you go about automating that? And there's several methodologies, general methodologies we'll talk about here. And the next series of slides covers those. This introduction to composites is not really focused on composites manufacturing. We have a separate module that talks about that and all the variables there. But in order to understand composites and what they do and how they work and some of the cost strength issues associated with composites, you really got to understand how they're put together. So this slide introduces the automated layup process, and in that there's a couple of methodologies here. One is on the left we have a robot or gantry type robot that's moving back and forth and laying down a strip of fabric or tape, a narrow fabric. And on the right side we have a machine that's actually rotating the part and the mold, or a mandrel, a male mold if you will. It's rotating that whole assembly around, and then a fixed or semi-movable applicator head is allowing that tape or fabric, or fibers rather, to be laid onto this male mold. So the two basic methodologies that we talked about in the previous slide, one has to do with a stationary, typically female mold that we're laying fabric or fibers into. So we have to move our application device. And the other has to do with a male mold that we're rotating in a way that we allow the material to be wound around this mandrel or male mold. So there's two ways that we can handle the material that we're going to lay out on this rotating mandrel. One is to use a tow. Remember we said a tow was a group of fibers together. These are typically long strand or continuous fibers, and so we pay those out from a reel and we rotate the mandrel, and as the mandrel rotates we lay the fibers onto it. And typically we wet those fibers. In these machines on the lower left and on the right, you'll see what looks like rollers that surround the fiber as it's coming out of the dispenser. And those rollers are actually a bath that put a little bit of resin onto the fibers so that they're tacked into place. So once we wind up all the fibers, they stay where we put them, and then typically you do a vacuum resin infusion process where we bag this whole part and we pull resin in around the fibers or the fabric material. In the instructor notes, we start out with the material that sets the stage for what course we're teaching and what we're going to cover in the course. Then we go individual slide and describe each slide, and you saw some of that. And at the bottom we have reference materials and other things that students can do. So if you actually want to spend 2 weeks on composites as opposed to 2 to 3 hours, we have materials that would allow you to quickly and easily go out and assign other things for your students to do, or if you want them to have out-of-class educational experiences. We also have a reference section that gives you references for you to go out and find additional material. These are things, reference materials that we've used in preparation of these classes and we know are high quality materials. For instance, the Society of Manufacturing Engineers puts out a great textbook on composites by Professor Brent Strong, and that's listed in our reference materials. We also like to include, and we do in the composites, we try to do this in all of our materials, vendor websites so that the students can go to the vendor's website and actually look for real materials and look at the specifications. What sort of decisions do you have to make in selecting one fabric over another fabric, or one resin over another resin? And so being able to go to the catalogs, to the websites, allows you to have a library of vendor materials available at your fingertips. Okay, so we have talked about, we presented a way that you can minimize your preparation time by using the slides and the PowerPoints that we have. We've talked about how we try to make those slides flexible in their usage. So we have PowerPoints with images and we have Word documents. You can take our PowerPoints if you'd like and substitute your images, or take our images and put in your words, however you'd like to do that. We would, obviously, we'd like for you to use ours as we've packaged them, because that introduces your students to the aerospace manufacturing piece of this. But it's for you to use. We've also given you in the instructor notes some additional materials, and part of that is videos of what you could call a laboratory. So that's analogous to having a strength of materials laboratory where you have a tensile test machine and you have 35 students in the lab. It's very difficult to have every student set up the machine and pull the tensile specimens and do the analysis. And so typically, or oftentimes, what we do is we have a demonstration where the instructor or an assistant actually pulls the tensile specimens and the students record the information and they go and do the analysis. You could argue back and forth if that, how effective that is. It would be more effective, though, I think we could all agree, if every student could set the machine up and pull his own tensile specimens, or even prepare his own tensile specimens. It's just the expense and the time won't allow us to do that. So we try to make a compromise and do the best thing we can. We were looking for ways to do composites labs to support this course. And obviously the pro there, the goal is for us to allow students to get this hands-on experience with the materials so that they can internalize that theory, so that they can understand how it actually works and feel that. The con is that composites labs tend to be dirty. They tend to require, most people use a dedicated lab space for that because of the types of materials that are used. And the materials themselves are expensive and in many cases require refrigeration to store them, so they don't have a long shelf life. Also, they're typically sold in fairly large quantities. And so if you buy the smallest quantities available, you may end up with enough materials for 5 years worth of labs, but your shelf life is only 6 months. So you end up wasting a lot of materials. How do you get around this? Well, One way to do that is to use the videos from the vendors that we've presented to you in the instructor notes. The other way, we went out looking and we looked for a way to do this that would mitigate the negative parts of the lab. So, in thinking about how we would do a laboratory, we wanted to come up with a way of doing labs that would fit into a wide variety of available space, available time, was inexpensive, and we could do it anywhere in the country or even anywhere in the world. So our design goals were that we wanted prepackaged or easily available materials. We wanted to have these laboratories tested on students in the real world, so that when you out there in Middle Georgia College, to pick one of my old alma maters, if an instructor at Middle Georgia College wanted to do this laboratory, we want to have a minimum of prep time. We don't want you to have to go buy materials, test it out, make sure it works, so that you ensure that your students get a good quality experience in a short laboratory time available. So it needs to be tested. It needs to have good documentation. You and your students need to be able to take our documentation and follow that and come up with the predicted results. It needs to have references. That is, we need to be able to go out and expand this experience. If students are curious and they want to go find additional information, you have a place to send them to. And it needs to be standalone. That is, we don't want to require that you have a wet laboratory available to you. It has to fit into available space and stand on its own. So our issue was finding the materials out there in some sort of kit form that was commercially available, that someone was manufacturing for a larger market, so it was cost effective, and the academic institutions that are part of this grant didn't have to worry about trying to build and sell those kits. So we found this kit from Aircraft Spruce. And Aircraft Spruce is a company that caters towards home-built aircraft, parts and supplies to do experimental and home-built aircraft. This kit has all the materials that you need to make fiberglass parts. It has the resin, it has the glass fibers, it has actually fabric in 2 different weaves. And so everything's there. It even has the gloves that you need to wear, latex gloves that you need to wear in mixing up the resin. So we experimented with this kit. It also has an interesting book in it too. Burt Rutan is one of the pioneers or one of the heroes in aerospace. And he wrote a book, essentially a do-it-yourself book, on how you go about building experimental aircraft or home-built aircraft parts out of composites. And this kit is built around his book so that you can actually build those parts without having to ruin very expensive parts that are made with stronger resins, for instance. So we took this kit, and we don't use Burt Rutan's text. It's an interesting book, but we don't use it because it's really going in a different direction. We write our own procedures, and those are available free online. You can download them. And if you use our procedures with this kit of parts, then you can run the labs and come up with a predictable result. Now, the basic kit is $80, and there's another $10 for if you want to have Burt Rutan's book included in it. Rutan's book is great. You don't have to have it, though, to do our labs. You can take one of these kits for $80 and it has enough material to do all 4 of our composite labs that we currently have out there for a class size of 15 to 20 students. And you can complete all of those labs using this one kit. So now you know what your fixed cost is for that block of laboratories inside your course. Now when we say labs, our labs are designed for 1 hour of student involvement, actual student hands-on. So the first 4 labs are 4 hours total, and they build one on top of the other. So you could do them, you could do 2 of them together and then do 2 later. There's some cure time in the middle. So this is a parts list for the components that are in this kit. And you can see they widely vary here. Everything from gloves to tape to the resin system to a spreader, a plastic piece of flat plastic that you use to spread the resin out. Everything you need to make parts is in here. The important thing here is that the resin system is always the same and the fibers are always the same. So an instructor in Georgia is using the same systems that the instructor in Oregon is using, and if you use the same procedure, you should come up with an equivalent result. First 3 labs, as I said before, there are 3 1-hour labs. And lab 1 is preparation, lab 2 is actual layup, and lab 3 is the testing. We feel that you miss something if you only do the layup and make a shape. Because in the real world, in manufacturing a part, you're manufacturing a part to a set of specs that say it's going to have a certain strength, right? It's going to have a certain surface quality. It's going to have a certain dimensional accuracy out there. And so if you don't do the testing part, you don't close that loop. And so this allows you to do simple parts. All 3 of these labs allow you to do simple parts and actually do strength testing so that you can compare manufacturing variables like the orientation of the fibers from one to another. So this is the introduction to the labs that's included in the lab write-up. It goes through and describes the materials that will be used, and then it describes the end result. What is it you're actually trying to accomplish? So the students are going to build test panels, and they're going to build those test panels using different weaves of fabric, and then they'll test those panels for rigidity. One of the things we tried to do in doing the testing part of this was to look for ways that we could characterize the different permutations in manufacturing without having to specify that you're going to have a tensile tester or you're going to have an impact tester, because these are expensive and space-using pieces of machinery that require maintenance. So if we can do this in a very simple way, then we can hit a much broader audience. So we use bending specimens where we clamp them to a table using a pair of vice grips and then load them using a plastic jug filled with varying amounts of water so we can vary the weight on it. So it's a very simple testing procedure, not very expensive testing procedure that can be done in a classroom. You don't have to have a laboratory environment. Actually making the composite materials can be done in a classroom. You got to be a little careful and cover things up and maybe split plastic garbage bags so that you can throw away the wastage and you don't mess up desks or tabletops. But it's certainly feasible to do it in a classroom. First of all, we've seen the limitation of the manufacturing process and the wet layup. That is, it's very time consuming to orient the fabrics in the proper direction and to apply the resin to the fabric. So we need to take that manual component out. So more automation is a key, and there's much work going on in more sophisticated, faster, automated procedures for laying down the fabric to make the parts. Embedded sensors and actuators. In the aircraft industry particularly, and also in the automotive industry, you're seeing more sensors embedded in, or telltales embedded into the composites. What do I mean by that? Well, if we put a transmitter embedded into the plastic resin that transmits a certain code that indicates this is a part of a fuselage or part of a wing, then it's very easy for us to inventory parts. And we don't have to apply a barcode or an external tag to this part. It's part of the part. It's built into it, and it never goes away. And so later on, if it's a military application, you have military airplanes, if you need to make sure that you're stocking certain replacement parts, you can quickly and easily tell for sure that you have that particular part in stock. There's also some work going on embedding sensors, strain transducers, into the skin or into the parts that comprise the skin or wing structure of an aircraft. So as we stress the aircraft, when we start to reach the stress limits, how can we record that automatically? There are G meters current production uses accelerometers mounted overall in the aircraft, but how can you tell how often you're flexing the wing structure in a way that will cause cumulative damage or cracking, fatigue damage in the resin? So we can embed sensors directly into the part at the stress risers and be able to track that and make more efficient use of the parts. And we can do this because it's a fairly low temperature manufacturing process to cure the resins out. Speaking of low temperature, the other piece that really stands out as a problem in manufacturing composites is the necessity to autoclave high performance parts. That is, to put them in these pressure vessels that are ovens, the autoclaves, to cure them out. So if we could come up with a sufficiently strong part without having to put it into a pressure vessel, then we've certainly speeded up the process and we've taken out a lot of expense. And so there's a lot of work going on in the aerospace industry for out of autoclave, or OOA, high performance materials. That's very promising. There are parts being made today that are going on commercial aircraft that are made out of autoclave that give performance levels consistent with what we were seeing with parts that had to be autoclaved a few years ago. So that concludes talking about the module itself. Now, as you look at an introduction to composites module versus an assembly module, you'll see some differences in style because of the type of material we're trying to present. But the basic structure is the same throughout all of our modules. So you have a PowerPoint. The formatting for the PowerPoint is the same throughout all of our modules. You have a set of instructor notes. The items that make up the instructor notes are the same throughout all of our modules. We encourage feedback from users. We'd like to improve this product, and so as you use our stuff, if you find something that we could do better, we encourage you to let us know, and we have a feedback mechanism built into our website that allows you to do that. We're also looking for new partners. We have 4 institutions now, 2 community colleges and 2 universities that are partners in this grant effort. We would like to continue this work, and we're looking for other academic partners out there to assist us in developing modules and to expand this out into other areas of aerospace manufacturing.